All right, we're in section 15.5 of our physics textbook. Chapter 15 is all about thermodynamics, and in this section we're specifically talking about heat engines. So here's a diagram of a heat engine where we have a steam engine. So we have a heat input that heats up this water and turns it into steam. So here we have our high temperature that comes down here, and it causes the piston to move and causes this crank to turn and is used to do work in some way. But not 100% of the heat energy goes into doing work. We do still have some, well, it's still relatively hot, but compared to the temperature coming in, it's cool, okay? And in fact, in this case, the steam comes into a condenser where it cools down even more and turns into water. And then the water gets pumped back up here, back into the starting reservoir, and the cycle repeats. So we have QH going in, we've got our work being done, and we have our Q low heat here. Here we have an internal combustion engine where the intake valve opens up. We have a gas-air mixture that comes in. The valves close, sealing off the cylinder. The piston comes up and compresses all those molecules together. It increases the pressure and decreases the volume. Then the spark plug ignites that. It pushes the piston back down and allows it to do work. This is the expansion here is the power stroke that does the work. So here's where we're developing our high heat. We do work, but not all of it does work. We still have some relatively hot exhaust gas. This valve opens up and it exhausts here. So this is our QL. So it might seem like, well, the exhaust gas is still pretty hot, which it is, but compared to the explosion itself, the initial combustion, it is pretty low in its heat. This is just kind of a question posed in the textbook. Why does a heat engine need a temperature difference? Why is that necessary? Why does it need to decrease in temperature? So temperature is a measure of the energy in a system. And so if the first law of thermodynamics says that the change in energy equals the heat flow in minus the work being done, if there's no change in temperature, then there's no work being done. This becomes zero. So in order to do work, there needs to be some change occurring between the heat flow in and the work out. Now we've been saying here that when you have a heat engine, you've got a high heat that goes in, it does some work, and then we have a byproduct, an exhaust, low temperature that comes out. Now, if we had a 100% efficient engine, all of this would do work and we wouldn't have any exhaust. But that's not reality. In reality, we need to have some type of low temperature going out. But the more work that can be done and the less amount of low heat coming out to the other end, the more efficient it will be. So we're going to introduce this idea of efficiency as the ratio of work over QH. So if the work was equal to the QH, if all of the QH became work and they were equal, we would have 1 over 1. We would have a 100% efficient engine. Okay, so we can rearrange this efficiency formula in several different ways. The work being done is equal to the high heat minus the low heat, and then these will cancel out to become 1. So we can write it as efficiency equals 1 minus low heat over high heat. So this is just another way of writing this same formula up here. And so let's take a look at an example problem that involves efficiency. So if an automobile has an efficiency of 20%, and I wouldn't be surprised if that's pretty accurate to what efficiency of a typical engine is, only about 20% is used to do work. That means the other 80% is going out the tailpipe. But if that produces 23,000 joules of mechanical work per second during its operation, how much heat input is required and how much heat is discharged as waste heat from the engine per second? Okay, so our efficiency is equal to the work being done compared to the heat that we put in. Okay, so if we wanted to solve this equation for the high heat, that's going to be equal to the work divided by the efficiency. So the high heat going into the system is equal to our work being done, which is 23,000 joules divided by our efficiency was 20% or 0.20. That's giving us 1.15 times 10 to the 5th joules. Or we could write that as 115 kilojoules is the high heat that needs to go into this car to make it run at this efficiency level. So the second part of the question wants to know how much heat is coming out the tailpipe as waste heat. There are a couple different ways you could look at this. The simplest way is probably if we are operating at 20% efficiency, that means that 80% is waste. So if we need to put into this system 115 kilojoules, then 80% of that is equal to 92 kilojoules. That's how much energy is coming out the tailpipe of this car. That's how much heat is not being used to actually make the car go. 80% of it is being wasted. So clearly there is room for improvement there. And engineers are always trying to improve the efficiency of an engine to make it run better, to use more of that energy, to do actual useful work rather than just simply being wasted. And that is what finally brings us to this idea of the Carnot engine. The Carnot engine is an ideal, perfect engine. It consists of completely isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Those are the 4 cycles of expansion and compression of the gas in a heat engine to do work. And if they are all running absolutely perfectly at 100% efficiency, you can calculate theoretically, if you put a certain amount of heat into an engine, how much work you can get out the other side. And Carnot was a Scottish scientist. And so the Carnot engine here, the reason why there's a unicorn on this slide is because Carnot engines don't actually exist. It's impossible to get away from friction in the real world. We cannot actually achieve a 100% efficient engine. And also, the unicorn is the official animal of Scotland. Okay, so if we look at the cycle of an engine, so if we start here at point A, and from A to B in a perfect Carnot engine, we are going to experience isothermal expansion. So the piston is going to come up, the volume is going to increase, and that means the pressure is going to go down. So pressure is going down, volume is going up, and we come down here from here to here at the same temperature, isothermal, no change in temperature. So we're staying along this curve for an isothermal expansion. Then we achieve an adiabatic expansion. Okay, so adiabatic means that we're not having any heat leaving our system. So if you remember when we talked about ideal gases, when you drop the pressure on a gas, when the pressure decreases, the temperature does as well. So we're going to see a drop. We're basically going to jump from this top curve here, on this curve here. We're going to jump down to this curve right here. So we're dropping to a lower temperature even though we don't have any heat leaving or entering our system. We're just going to drop to the lower temperature because of expansion of the volume. Then we're going to have isothermal compression. We're going to keep the temperature the same, but this time the piston is going to come down and compress the gas. So the volume is going to go down. We're going to go to the left, but we're also going to start to go up. The pressure is going to begin to increase. Then we will have adiabatic compression. And again, when you compress a gas, you increase its temperature. So we're going to jump from this lower curve back up to the higher curve, and we're back to our starting point. And so if we keep following around and around in this cycle, this is the perfect Carnot cycle. So a perfectly ideal engine would follow this path. So what Carnot came up with is this formula that for the efficiency of an ideal engine running at the best it possibly can would be the temperature, the high temperature minus the low temperature divided by the high temperature. So in other words, if the low temperature here was 0, if we weren't wasting any temperature, if we're using all the heat that goes into the system to do the work, this would become 1 minus 0, or 100% efficiency. Sounds great, right? We should start building Carnot engines today. Why can't we do that, though? Well, because think about this. This means that the temperature has to be 0. And we're not talking Celsius here. We're talking Kelvin. So that means that it has to get all the way down to absolute 0. So our cold reservoir has to be absolute 0, and we can't achieve that. That's not really physically possible, or at least not practically possible. So because of that, a Carnot engine cannot exist. It is the ideal. It's what engineers would love to achieve and try to get as close to as possible, but it can't actually ever be achieved.